Hello everyone, this is Ankita Rajput and welcome to 4Pi Academy classes. So today we will discuss everything about basic of spatial theory of relativity. Okay, that's very important topic in physics. So let's start. So if we talk about spatial theory of relativity, this is the very first equation. This is the very first thing which comes in our mind. Okay, E equals to mc square. That is the main uh, gist behind the spatial theory of relativity. E equals to mc square. And even if some person doesn't have very much knowledge of physics, but he might have heard about this equation. Okay, so we can understand how important and how famous this spatial theory of relativity is. So this theory was developed or discovered by the very great Albert Einstein in 1905. And what this theory basically tells us, this theory tells us that how space and time are related for the objects that are moving at a consistent speed. Okay, so this is the spatial theory of relativity, and these are the basic postulates of spatial theory of relativity on which the complete whole spatial theory of relativity is based. Okay, so very first law or postulate we should say of spatial theory of relativity is all the laws in physics are invariant in all inertial frames of references. All laws of physics means in your school you heard about Newton's law, gravitational laws, all other basic laws. So all the basic laws of physics are remain invariant in all inertial frame of references. And this term inertial frame of references are basically the non-accelerated frame of references. Okay, we will discuss in detail in our upcoming slides what are the inertial and non-inertial frame of references. Okay, so what is the very first postulate of STR? That all the basic laws of physics are invariant in all inertial frames of references. The second postulate is speed of light in vacuum is same for all observers regardless of the motion of the light source or observer. Means if you are getting light from a bulb, tube light, we can say candle or sunlight or something, it doesn't matter at all from which light source the light is coming, but its speed inside the vacuum will remain same. Okay, that is C. So this is the second postulate of spatial theory of relativity. Let us discuss about inertial frame of references. Okay, so a reference frame in which we can say Newton's first law is valid. What is the Newton's first law? You all know Newton's first law of motion. Newton's first law tells if a body is at rest or it is moving with a constant velocity unless another force acts upon it. So this is the first law of Newton. So the frame of references in which this condition is applicable means these frame of references follow the Newton's first law of motion. Okay, so this is the example of inertial frame of references. What a person inside a stationary car, you can see this is a stationary car, it is at rest, and a person is sitting inside this car. So this is the example of inertial frame of references because the body or object is in rest. Okay, and there is no external force working on it. Okay, so this is the example of inertial frame of references. The second category is non-inertial frame of references. So these frames are just opposite of inertial frame of references. Means what? These are basically these inertial frames are don't follow Newton's first law, means there will be some external force which will work upon it. Okay, so these are accelerated frames of references and inertial frames are non-inertial non-accelerated frame of references. An example of non-inertial frame of reference, like you can see in this image, this car is moving. Okay, this is an accelerating car. Okay, its speed or velocity is continuously increasing and a person is sitting inside this car. So when the speed of this car is increasing, means some acceleration is coming into picture. So due to this acceleration, the person inside this car will feel that it is going backward, means the accelerating car will push this person back into the seat. So this is an example of non-inertial frame of reference. If you are still confused about how to distinguish whether it's a inertial frame or non-inertial frame of references, what is the difference between both these frame of references, so this picture will give you the better understanding. Okay, so let us say this is your train, and in this train two person P and Q are sitting. Okay, and a third person R is standing or sitting outside the train. Okay, and the car is moving with velocity v in negative x direction. Okay, so for this person P, this person Q is at rest, right? Because both these person are inside the train. So for person P, for person Q will be at rest, but for person R, which is outside the train, which is standing outside the train, this person Q will be traveling in the same direction as the train is moving. Okay, so we can say inertial frame is also relative. Means what? So how we can figure out which is inertial frame? So first, listen carefully. First, we need to assume an inertial frame or a reference frame for us before going further. Means if we are saying that this person is at rest, so we are saying this in reference to us, like in reference to ourselves, we are saying that this person is at rest. Okay, and this person is also at rest. Okay, so before distinguishing or telling that which is inertial or non-inertial frame, first we need to assume an inertial frame for us, means a reference frame. Okay, जिसके respect में we can figure out whether this is moving or at rest, right? So a frame is said to be inertial if it is at rest or moving with constant velocity with respect to our assumed inertial frame or reference frame. Okay, so here P is inertial frame for Q, because both P and Q are in the same frame. So P will be inertial frame for Q and Q will be inertial frame for P. But this P is non-inertial frame for R. Okay, so this is how we should figure out inertial and non-inertial frame of references. Okay, so now let us discuss about some length contraction, how length is contracted in spatial theory of relativity. So suppose a body is traveling with a speed which is relative to the velocity of light. Okay, then only relativity comes in picture. If we are talking about this, some body is traveling with some velocity v, and that v is very, very smaller than c, then generally we don't talk about a spatial theory of relativity, because in this case the contraction or the change in length will be so small then that we cannot calculate or tell the difference. Okay, so only in the cases where speed is relative to the velocity of light, this relativity comes into picture. Okay, so let us say proper length of an object is L0 in stationary frame, right? And L is the length in some moving frame with respect to stationary frame. Then relativity says that length L would appear to be contracted, means length is appear to be reduced from the original length. Okay, and the formula is given by this equation. L equals to L0 1 minus v square over c square. L is the length in the moving frame and L0 is the original length in the stationary frame. V is the velocity from which your object is moving and c is of course the speed of light. So this equation tells you that L will be less than L0, right? So now let us see one more important thing in length contraction. So suppose this is your body, okay, and it is at rest. Okay, and we can say that this is the proper length or proper dimension. So suppose this is L0. Okay, suppose this is your L0. Now what? Now the speed is increasing. Now v is now 0.3 c, means your object is now moving with some velocity v equals to 0.3 c. And one more thing, the motion is in the direction, this direction. Okay, so the contraction in length will only be in this direction only, means now you can see in this image, in this body, this length is now less than this length L0. Suppose this is now L, so L is less than L0, so we can see the reduction is taking place in this direction, which is a direction parallel to the direction of motion. There is no change in this direction because it's same, right? And again, if velocity is further increased, v equals to 0.6 c, now we can see the length is now further reduced. The length is now further reduced. This L is, suppose this is L dash, so this L dash is less than this L, right? Again, if now v is 0.8 c, higher than the previous case, so we can see further the length is further reduced. This, so what this these images are telling you, the images are telling you that the contraction is in the parallel direction of motion. There is no contraction in the perpendicular direction of motion, and as v is increasing and v is approaching towards c, the contraction will be higher and higher. Okay, so this is the length contraction. Now let us see what is the time dilation, because it's also a very important topic in spatial theory of relativity. So suppose if we have two clocks and these clocks are moving relative to each other and they both measured time for a particular event in their respective frames. So the difference in the time observed by both these clocks is known as time dilation. So suppose for particular event, delta t naught is the time observed by observer in inertial frame S, and delta t is that time observed by the observer which is in non-inertial frame S dash. Okay, and this S dash is moving with velocity v relative to this frame S. So delta t will be delta t naught upon under root 1 minus v square upon c square, means these two times delta t and delta t naught are related with this equation, and this equation will tell you that delta t is greater than delta t naught, means time is dilated, time is appear to be increased. Okay, so this is the time dilation. So let us see this slide. This will give you the more understanding, more insight about the time dilation. So suppose this is the car and this car is moving with velocity v, and this is some clock, this is some clock which is attached to this car. Okay, and initially this car is at rest. Okay, and there is another clock which is standing on road. Okay, so initially when this car is at rest, we can see these two clocks are showing the same time. Okay, but now what? If car is moving with velocity v, okay, towards this clock, so now we can clearly observe that the time shown by both the clocks are different, and we can see that this clock is appear to be slow. Okay, it is showing that time is less, so it is slow now as compared to this standing clock. So it means what? An observer which is in inertial frame determines that the clock in motion related to the observer's clock slower than the observer's own clock. Okay, and we are saying so okay, it's clear that the clock in the motion will be slow, right? And second point, what we observed, that we are saying that time is dilated, time is increased. So means for the same thing, it is taking longer time. It's slow, so it is taking longer time, na? So time is dilated. So time is dilated in spatial theory of relativity. Now one more important topic in this video is relativity of simultaneity. So what is this relativity of simultaneity? So two separated events occurring at the same time is not absolute. It depends on observers' frames. Means what? If we have two different events, suppose A and B are two different events, and these events are occurring at the same time, okay, in inertial frame, so it is not absolute. It means it will depend on observer's frame. Okay, so see what, suppose A and B are two events, and A and B are happening in are in the same frame, okay, and their positions are x1 and x2, and let us say P is a person which is in the same frame of A and B. So P will observe that these two events A and B, these events are occurring at the same time, right? Because P is in the same frame of reference. Now what? Some person Q is inside the plane, and plane is moving with velocity v. So for this person Q, the two events A and B are not simultaneous. PQ will observe that these two events will occur with some time difference, and that is the relativity of simultaneity. And so A and B are simultaneous events for person P, right? But for person Q, A and B are not simultaneous, and this time difference is given by this equation, V upon C square x2 minus x1 upon 1 minus V square over C square. Okay, so this is relativity of simultaneity, guys. So thanks for watching this video, and in this video of special theory of relativity, we try to cover the basics and important topic of STR. Okay, and we will very soon we will come with other topics of special theory of relativity in our upcoming video. So till then, keep learning. Thanks.